Hi, now we're going to create an actual encryption system. And where we're going to start is we're going to create some keys that we're going to encrypt against. I don't know if you saw the principles video. It's not that important, but we're building on the RSA model. And in order to do this, we've got a script written. What this guy is going to do is start off with some Python standard module, sys, and random. We're going to use random number a lot. It's important to get it's close to real random number, not pseudo-random numbers. Uh, as we can when we generate the prime numbers and the e values. Anyway, I'm going to use math functions down here. I'm called up here and down there as well, but I'm going to call generate bits. I'm going to say how many bits are in a number that we generate. They'll tell us what the key strength is. Function for square root for really big numbers. A faster version of the greatest common divisor, and from primes to generate primes. And each one of these are pretty simple functions. The math function, most important here, is to generate keys. We're going to ask it to go off. We're going to pass it a prime number and another prime number, and it's going to go through and create your PQ, sometimes known as N, your phi function, which is the totient that you're going to find E, the encryptor, and D, the decryptor from. And there you have it. So you have the generate keys. Coming back, we're just going to generate a key. I'm just going to walk through this main function. What it's going to be sent are basically two things that we want to make sure we get in here, and that's p length and q length, and that's the digit length of the prime number, p and the q. The other variables here that we're passing on aren't necessarily that important. If you want to have deterministic, absolutely have a prime instead of a very probable prime, set that to true. It'll take longer for the prime number and then therefore the key to generate. Number of tests, the higher that is, the better the chance that the probable prime is prime. 20 is good enough for this demonstration. It depends on the length of the prime. That's going to guarantee that that's prime. Anyway, max attempts is just a counter that we're going to do to make sure we get the right distance and other things. We're just going to use it as a general count for trying things over and over again. So we're going to get in this function. There's a sub function here called get prime sub function, so use it twice to get different primes. I don't want to copy the code over and over again. Anyway, the first thing we're going to do is get the payload and the result. I don't know if I actually use the results here, but the payload is going to be basically the key that we're going to generate. I'm going to seed it was 1 and 1 and 0, 0, but basically nothing, this initialized. And I'm going to get my first prime, the prime of p length, and that's the prime I'm going to use through the whole routine. So the next thing we want to get is a q. So instead of just getting q by itself, I could just say q and get the prime. But there's a couple things we want to make sure of to make it less breakable, less factorable. And what that is going to make sure that the greatest common divisor between q minus 1 and p minus 1 is 2, basically. This is going to loop until it's while it's not 2, and once it's 2, it's going to figure it out. So that's just to make sure that p and q are basically far enough apart. And let's see what we have. We got the get q right here, and this is the value. We want the absolute value of p minus q to be greater than the value, which is determined by 1 plus 2 times the square root, the fourth root of p and q. And if p and q are really close together, I guess it's easier for somebody to factor that. So we want to make sure. You could also just skip that part and say, hey, I want p to be 100 digits and q to be 101 digits, and that would work too. This stuff will slow things down if things are closer. Not so much this one, but another one that's coming up. So, and I set it to q equals 1 if it doesn't make it through, and if it doesn't go through max number of attempt counts, it comes over and says if q is equals 1, I failed, and I bump out of here and I failed to generate the key. The next thing you want to do is get a valid E. And a valid E sounds so, how do you say, so melodious. And as I note here, we want this E to be greater than 1 plus again, the fourth root of PQ divided by 3. I've referenced a guy who says this is why. So it's a pretty big equation. So I have to break it out. So break it into parts so that Python can deal with it. Get that square root function there that deals with really big numbers. You do this math module square root, you're going to get a float. I need this to be in integers. So we're going to go and get that PSQS, multiply it and get the limit. And if max is greater than the D limit, where did I define D limit? Oh, it's right above. Sorry, this. And the keys don't equal each other. Then we're cool. We can break out of that loop. Arbitrary count of 100. That will slow things down for sure. I don't know why I didn't put max attempts on there. Who knows? This will slow it down. I mean, you could just pick an E that's arbitrarily bigger than Q and be done with it, and then move on with your life. But I didn't do that, so there you go. I just put P and Q therefore into the payload dictionary, and then as I'm looking at this to see what I did, I think I have to get D. Where did I get D? Let's just figure this out. Keys D. Oh, I'm getting max D up there. I'm sorry, guys. I'm totally spacing this. Oh, I ran the generate keys right there. Generate keys gets E and D, and we just had to make sure E is particularly suitable for that. So obviously, we can max it E or D. Normally, you give this the lower encryption to the end user because it's easier for the backend system to encrypt a smaller number, I guess. Some people pick 3. Some people pick a Vermont prime that's 65,000 something. I'm just going free wild. These are actual random kind of E's and D's. Sorry, I'm rambling on that. But anyway, I get the E and D. And the whole point of that is just to get an ED and a key load. And then I update the keys right there. I don't know if I'm making sense at this point, but I'm going to update the payload with the keys that I just pulled off with keys. And then I'm going to get the bit, number of bits. And I'm going to put a breakpoint there. We're going to run this. And the digit length. And the bits are going to be, like you see, you want encryption that's greater than 124 bits or 248 bits. And this is just going to give you the bit size of PQ. And that's returns results. And you end up with a key that you can now encrypt against. This other function is just a wrapper that takes that generate key, that will scroll up really fast, get new key function, and it creates n number of them over, the random P, Q length, and then returns them back. We'll use this later in our key management system. But for right now, what I'm going to do is I'm going to put a breakpoint here and run this guy. And by running that, it should, did I click run? I can't. Move away. Let's try that again. Okay, there it is. It made it. I'm going to say I'm going to P length of 10. Okay, I'm making it real easy the first time. I'll just walk through it. So I'm going to print get keys. So I'm going to come in here, get the copy. Here's my payload, get a prime. My first prime is, let's look at it with a hover over. It's 633 whatever, 10 digits, not a really big prime. And then I'm going to get a Q, and there Q is that guy right there. Now I want to make sure that while the fast, I want to call it fast, is a faster greatest common divisor. It's a faster algorithm than I think it's the Euclid one, but it'll just keep getting a Q until it finds it. And these are, oh, it found one. So it broke out of there. Sometimes, the smaller the numbers, the more options that they're going to be, more chances they're going to be close together. You get hundreds and 500 digit prime numbers. That's not going to happen that often. Anyway, it could slow it down up to n number of max attempt times. Okay, that guy right there. All right. So now we're going to go see. Now that we got this first condition where it equals to, it has the greatest common divisor as small as possible, and make sure that they're far enough apart, and they appear to be, so we broke out of that. And it's not 1 because it doesn't fail. So we now have our prime numbers, the P and the Q. So now we're going to get the E. So we're going to ask it to generate keys. And if I look here, the generate keys says it's like this thing right there. In fact, I'll even come over to debug and say, where are my keys? Yeah, so 2 10-digit numbers, E and D. If this is going to be successful, that's going to be your public key, and then
that is going to be your private key. I'm going to pick the max of E and D, and I'm going to do that one equation that Michael Wiener says is important, and it passed it, so I can break out of this 100 count. Yeah, I'm going to put my payload. I'm going to make sure that everything looks okay in terms of the keys aren't. Yeah, this happens. This right there. If E and D equals the same thing, that's bad. Your encryption and decryption are the same. This is only really going to happen if you have like 2-digit primes or 3 really small digit primes. If you have hundreds of digits, the chances of that happening are astronomically small. But might as well check for it anyway, right? And if keys come up with bad keys less than 1, that's something errored out. We'll just hey, no inverse found or whatever. So I'm going to update payload with the keys. And I'm going to say payload key bits and payload the distance, or sorry, the digit length. So if I say payload, now at this point, I have all this stuff in there. I have my primary key, my primary key on the database, the P prime, the Q prime, the digit of P times Q length, the bits, so it's 66 bits key, not very secure. PQ is there, and there's our E and our E. I'm going to post that to my results, because I always return a result, come back up, and it prints it out to standard out. Same thing, right? As always. Return code of true. Maybe it's just a RC instead of return code. I don't know. No message because there's no error in this case. And here's my payload, which is the full key with information about it. I mean, something you won't want to pass that to the user. You want to break out E from D at least, and don't definitely maybe just in yours just throw away P and Q at this point. You don't want anybody to know that. Okay, then this thing goes off and generates 10 keys to demonstrate the whole thing of it, and get an idea. Let's take off the breakpoints and let it run, and bam. I say bam and expect it to be done, but 10 keys could take a little bit. Your hardware is going to make a difference. Not having it in the IDE will certainly make it go faster. You can go and modify your different. There's my pretended. Just you can modify your restrictions up here. This is going to slow it down, particularly this validating your E stuff, and did the research on this to make sure that the stuff I even quoted a person. So anyway, this should come out eventually and print all the keys. Let's put a breakpoint on it and wait for it. Well, this is taking a little bit of time. Let's go see what we're asking. We're asking generate 10 keys. I just realized that 10 keys, and I didn't tell it how much. So they're going to be between 200 and 500 digit long. So that's going to take a little bit of time for it to go through just even 10 with the restrictions. So you take those restrictions off, this thing gets done in like 30 seconds. Anyway, I'll put it on pause while this does that. And here it finally got up. So let's just take that breakpoint off so it doesn't rotate across the. Am I actually working here? Hello? Okay, sorry guys. Hi. I will edit this out. Okay, so it caught to the breakpoint. I'm going to take the breakpoint off so that it processed those larger primes. And I'm just going to print it through and show you that here are the keys it generated. Wham! Look at that. It did it. Now, assuming I did my stuff right, these keys are now usable for encryption, and we can start to go ahead and create the next step.